start the last session of the morning. Last talk of the morning session. So our next speaker is Professor Tom Goldstein from the University of Maryland. He really doesn't need introduction. I think we all know his earlier very influential work on the optimization of deep networks. Recently, he also has many interesting work on the safety and privacy of these models we currently have, and that's of interest to many of us here. Today in this talk, he will talk to us about reasoning and weak to strong generalization. Please.
All right, thank you very much. Okay, so when I submitted the title for this talk, I said recurrence as a mechanism for weak to strong generalization, which is a very wordy title, but maybe a better way to think about this is this talk is really about studying test time scaling without using language models. So this morning we saw Noam Brown's talk. He was talking about scaling up test time compute as a way to improve model performance. And one of the questions we all ask is, how do we study this sort of thing in an academic setting? If we don't have access to millions of dollars of compute, how do we do this? And I think that we can do this. We can come up with nice test problems where we can actually observe really strong, increases in performance by scaling up test time behaviors. We can observe weak to strong generalization. We can observe all sorts of things at a scale that we can actually do fundamental research with in an academic lab. Okay, so what motivates this kind of research is that humans are really good at what I call logical extrapolation, which means that you learn to solve simple logical reasoning problems, and then humans are really good at synthesizing more complex strategies that allow them to solve harder problems. For example, you might train a student to prove theorems, and then if they're a strong enough student, you might give them a really hard theorem, more difficult than anything they've seen before, and they'll figure out how to prove that, but they have to scale up the amount of test time compute. They have to think for a long time. It might be more difficult for them to solve this, but by exerting more cognitive effort, they can solve this problem. Humans also learn to play games with really low complexity. Systems like AlphaGo learn to play chess through millions of episodes. They play billions of episodes. They play billions of games, whereas a professional human chess player has only played tens of thousands of games in their entire life. But that's because humans are good at learning simple rules and then synthesizing more complex strategies by putting those rules together by thinking for longer. And humans are also really good at causality determination. We're good at thinking through different sequences of causes and effects and chaining those together, right? And so I think these are all like logical extrapolation behaviors that humans have. And so a couple of years ago, I got interested in this question of, can neural networks exhibit logical extrapolation? So to put that differently, I want a neural net that can solve harder problems than it was trained on. Nowadays, people might call this weak to strong generalization, although there might be a subtle difference here. When weak to strong generalization, you typically train a stronger model on the outputs of a weaker model at a data set, whereas easy to strong, there's what's called easy to hard generalization, where you train on easy problems and then you test on hard problems. On some level, these are both the same things. It's just that when you're doing weak to strong, you're typically training on a data set that was generated by a weaker model. Either way, what you're really interested in is training on some sort of weak data set and then training a very strong model that can exceed at problems that go beyond the difficulty of what is represented in that data set. Okay, so I want to study weak to strong generalization. I've been interested in this problem for a while, but I had some ideas that I was really motivated by, but I'm poor. At least I'm GPU poor. I don't have the compute to train a language model to observe these kinds of behaviors. So what can we do? It turns out that you can study these problems if you just formulate them correctly. So here's an overview of what we're going to talk about. I'm going to talk about reasoning problems that exhibit significant weak to strong behavior that is observable without large language models. Then I'm going to talk about architectures and training paradigms that enable weak to strong generalization that we've been able to develop by working with these sorts of toy problems. And then finally, I'll talk about trying to get these strategies to work with transformers, maybe not training them from scratch on huge corpuses of text, but at least on a toy language. So on languages involving arithmetic, you can actually observe fairly good weak to strong generalization if you use the kinds of methods that we develop working with these even more toyish problems. So there's a long literature on weak to strong generalization now, or maybe not super long, but there's at least a few different approaches. Most of what people are familiar with are distillation-based approaches. You have a weak model label a data set, and then you train another model on that data set. I think people have gotten really interested in this because of this 2023 paper on where they coined this term weak to strong generalization. But actually, this approach existed back in 2019, where people were using self-distillation to improve computer vision models. And then there are other kinds of inference time methods. There's work that was done on OpenAI with the O1 model. That's what you heard about this morning. And even before that, there's other kinds of methods that are trying to improve test time performance. For example, having a debate between different kinds of models. So there are distillation-based methods. There's inference-based methods. This is something that's sort of outside of those two that I'm interested in. I'm interested in recurrence. I want to have recurrent models, and I want to try to use recurrence as a mechanism to observe weak to strong generalization. And the motivation for this is that humans seem to have some sort of recurrent process that they use to solve difficult logical reasoning problems. We can take a problem, we can represent it in our memory, and then we can think about it over time. For humans, thinking and reasoning are temporal processes, and I think that temporal aspect is really important. Back in the 70s, philosophers would have said we have some sort of central executive unit that executes this kind of reasoning process. I don't quite know what that reasoning process is, but I think most people agree that these kind of slow thinking processes that humans have the temporal aspect is really important. We also point out we do have machines that can solve problems of, in some cases, arbitrary difficulty and can exhibit weak to strong behavior, but those are typically algorithms. We have algorithms that can solve, say, a sorting problem of arbitrary size, right? And we typically, those algorithms have some sort of recurrent mechanism inside of them. There's some sort of for loop kind of thing that executes over and over again. And if you want to solve a hard enough problem, you just have to run that for loop for a very, very long time. And so I would like to be able to have this kind of algorithmic learning behavior inside of neural networks, but I don't want it to have to be a handcrafted algorithm. I want it to be something that is learned end to end to solve problems in whatever domain, potentially a complicated unstructured domain, the neural net lives in. And so to study these problems, we are going to look at recurrent networks. To get down to brass tacks, that's all the philosophy stuff. Here's the basic idea. I want to train a neural network on easy problems, and I'm going to train it like this. I give it an easy problem like a maze. I want it to solve this maze. And I'm going to put that through a feature extractor, and then that feature extractor is going to stuff some features into a recurrent unit, which is just a block of the neural network that runs over and over and over again. You take the output of that block, and you feed it back in. You take the output, you feed it back in. You take the output, you feed it back in. You can run that as many times as you want. At train time, I'm going to run it 30 times in almost all the experiments that you see. So you get to run this 30 times at training time, and then you extract the solution using some feature extractor unit, and you have a label, which is the solution to this maze. And I want to train this entire thing end to end so that if I put in this easy problem, it produces the easy solution after going through 30 units of recurrence. All right, so I'm going to train this end to end. And then at test time, I'm going to give it a hard problem, maybe like a difficult maze, and I'm going to let it think for longer. So maybe I'll run this for 3,000 loops. Maybe I'll run this for 30,000 loops. I'm just going to let this recurrent unit run as long as it needs to run, and then I'm going to see whether the neural network can figure out how to solve a harder problem than it was trained on, just by letting it think for longer. Right? So if you want to implement this paradigm, step one is you have to replace feed-forward computation with recurrent computation. I think I've already sort of explained that, but just to be very clear, a typical feed-forward network, when I talk about feed-forward, I mean a network where you have layer 1, layer 2, layer 3, layer 4, layer 5, and then you extract the solution. And every layer gets used once and then tossed away. When I say a recurrent network, I mean something like this. You have layer A, and then you have B, 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 same layer over and over again, and then you have this final output layer. In some cases, this means that when we formulate a recurrent model, it will actually have fewer parameters than the original model. And I'll mention some interesting cases where that occurs later. But despite that, these recurrent models will actually oftentimes have much more powerful behaviors than their feed-forward counterparts, despite having fewer parameters. Okay, so that's the architecture. And I'll mention that all the experiments I'm about to show are with convnets. We give it 2D inputs, and we use a convnet. Later, I'll talk about transformers. So step two is let's train on easy problems, and let's crank up the hardness at test time, and let's see what happens. All right, so I'm going to train on things that look like this. I'm going to train on 9x9 mazes. Every maze is just given to the convnet as a 3-color image, an RGB image. It's got a green starting dot and a red ending dot, and the maze is represented in black and white. and I'm going to train the neural network to reproduce this label that I give to the neural network as a segmentation map that shows what the solution to the maze is. Then I'm going to test it on 13 by 13 mazes. So I'm going to see if this can make a generalization leap and solve a problem that is harder in some sense than the things that it was trained on. So here's what happens. We're going to start doing inference on these 13 by 13 mazes, and I'm going to let the number of test time iterations go up and up and up. This blue dotted line here is what you get with the best feed-forward network. We hyperparameter search this over different depths and widths and hyperparameters at training time. This is the best performance we get on those 13 by 13 mazes with a feed-forward net. But with a recurrent net, you can control how many test time iterations there are. You can't do that with a feed-forward net. That's why I just put this as a flat dotted line. And if we let this thing run for a while, we find that it keeps getting better and better the more iterations you give it. It was trained with 30 iterations. That's what this little gray box represents. This is the training regime. You surpass the feed-forward model pretty quickly. By the time you get to the 30 iterations you train on, you're already performing much better than a feed-forward model. And what's interesting is that if you keep going outside of the training regime, so we only train with 30 iterations, but if you give this more test time compute, this actually keeps going up, and you keep solving more and more of these mazes. But then it crashes. So if you let it run for too long, it overthinks, and the whole thing melts down, and it does considerably worse. So there's a limit to how far you can go. So this is what we had in our first paper. We trained on 9 by 9. We could test on 13 by 13. Reviewers were not super impressed by this paper. I kind of liked that result. I thought there was a glimmer of hope, but the reviewers weren't too impressed by that. So we went back to the drawing board, and we decided to make some architecture improvements. And here's one of the architecture improvements that we made. So in our original implementation, we just swapped feed-forward for a recurrent network. But a recurrent network is fundamentally bad because the parameters in these recurrent units are kind of noisy. And what you're basically doing is you're reading from memory, you're computing some stuff through this recurrent unit, and then you're writing back to memory. And then you read from memory, and you compute some stuff, and you write back. And you're reading, you write, and you're reading, you write. It's like every time you do this, you have to store all the information about the problem you're trying to solve in the state that the neural network has. And you read from that state, and you write back to it. You're basically making a copy of a copy of a copy. And once you've done that a few hundred times, your copy is pretty bad. Right? So we want to fix this. So we decided to implement these recall connections. I'll point out there's also a great paper from a team at CMU where they do something similar. They call this input injection. We call it recall connection, same thing. Well, the idea is that we have a skip connection where features from the input problem are stuffed into these recurrent units every time they run. And what this does is it prevents you from forgetting the problem you're trying to solve. It also prevents these recurrent units from losing information. So if some information gets lost because of noise in the computation, it's always possible to regenerate that information later on. And so that actually improves things a lot. So now, if we do the same experiment we had before, so I'm going to train on 9 by 9, and I'm going to test on 13 by 13. Before we had this problem where we would overthink, and now we don't overthink. We just keep running and running and running. We eventually saturate at 100%, and you solve all of these mazes. Right? So when we got to 100%, the next natural question is, how big can you go? Can you solve problems that are way harder than 9 by 9? So we wanted to try to scale this up and see what kind of problems are solvable this way. So here's the setup again. We're going to train on 9 by 9 mazes. We're going to train for 30 iterations, and this is the entire training set. All the mazes are 9 by 9. During the train time, we always use 30 iterations. That's what we use. And then we're going to test on big things. So we can test on, here's a 201 by 201 maze, and it will solve this, but you have to give it 2,400 iterations to do it. But it is able to solve this problem. You just have to give it about 100 times more compute power than it had at training time. All right, so yeah, you can generalize from weak to strong in a pretty dramatic way with these kinds of toy problems, right? But the point here is you don't need language models to study weak to strong. You can train on very simple things, and with the right architectures and the right training loops and the right kind of model design, you can actually observe pretty dramatic generalization. Here's the solution to that maze, by the way. So kind of a convoluted solution. But I wanted to know what's the biggest maze that we could solve, and so I had my student Avi load up the biggest maze that would fit on his card. And there's a green dot here where you start. There's a red dot here at the end. And this is a zoom in of the maze. This is the maze that he's solving. It's the maze that would fit in his card at the time. This is an 801 by 801 maze. And if you train only on 9 by 9 mazes, you can solve this problem. but it takes a lot of test time compute to generate the solution. It takes 20,000 iterations at test time, and our iterative block tree has about 5 convolutions in it, so this is actually a little over 100,000 conv layers that it takes to solve this, but you can solve this. You can get pretty dramatic weak to strong generalization. I'm actually pretty convinced that this network can solve a maze of any size with enough compute. It's just a matter of how much memory you have and how you run your implementation. Yeah. These mazes only have one solution. There's this, I mentioned that CMU paper. One of the things they look at is they look at multi-solution mazes. But you have to change a few things about the implementation to make that work. Okay, so one thing that Noam mentioned this morning is chain of thought models can do some interesting things. They can try different strategies. They can backtrack. They can error correct. But what's interesting is that you can actually get those behaviors without having to use train of thought. You can actually learn these behaviors end-to-end through recurrence. I'm not a huge fan of using chain of thought to do this, and I'll explain why at the end of the talk. I don't like chain of thought so much. But you can get these kind of behaviors without having to train on handcrafted chain of thought data. You can get it just by end-to-end training. So here's some demonstrations of this. If we run our recurrence solver on a maze, so I'll give the neural network a maze. Here's the start point, here's the end point. And we're going to let it run. And after every recurrence, I'm going to run that solution extractor, and I'm going to see what the solution looks like. And you actually get a visualizable solution, and you can actually see what's going on. It turns out that it's learned an algorithm. It's a classical parallel algorithm for mazes called dead-end filling. It's doing that. So it's doing something interpretable. But if you, I guess, mess with the algorithm, it will actually switch strategies to try to solve the problem in a different way. So I'm going to let this solve, and halfway through, I'm going to add a huge amount of Gaussian noise to the memory states. So add all this noise to the memory states, and then I extract the solution, and it looks like this. But if I let it run from this state, it will actually error correct its memory, and then it will converge to a solution of the original problem, but using an algorithm that appears to be different from dead-end filling. And then if I let it solve this maze, but then I move the green and the red dots, so after the maze is solved, I'll just swap the problem. I'll move the green and the red dots, and I'll let it keep cranking away. Then it will, so I have these new green and red positions. It will modify its maze. It will do a walk from the green dot toward the red dot without moving in any wrong directions. And it backtracks on this path from the red dot until they meet in the middle, and then it converges to a solution of the maze. And so these kinds of networks can actually have really interesting behaviors, like pretty complex behaviors that you can observe without having to study this in a language model setting. So we got interested in some more challenging problems. This is chess. On chess, we got a. I was interested in working on this problem. I didn't think any of my students would be into it, and then it turned out some of my students were really into chess and wanted to do this. One of them is Eitan Bordia, who's sitting in the audience right over here. We had students that really want to work on this, and so we got this catalog of chess puzzles, and we formatted them by giving we give the network an image of the chess puzzle, and then we wanted to output a map with 2 squares highlighted. You have the square for the piece that needs to move, and you have the square for the location that it's going to move to. And so we took a bunch of chess puzzles. We split it up into chunks. We took 600 easy chess puzzles to train on that, and then we held out 100 hard ELO score chess puzzles to test on those. And we want to see if it could make a bit of a leap. We do observe a leap in generalization, though not as dramatically as we did for mazes. So this is the best feed-forward model we can get. This is the blue dotted line again. And then if you use a recurrent model without those fancy skip connections, it will actually do considerably better than the feed-forward, but it will melt down before you leave the training regime. And then if you implement this with those skip connections, you get this nice behavior again where it converges to steady state solutions. And if you let it run outside the training regime, it'll actually continue to solve more chess puzzles, more chess puzzles than it could inside the training regime. And it's just a nifty visualization of this. So here's a chess puzzle, not a super hard one, but the solution is you want to move a rook from here to here. And so when you start iterating, at first the output is just sort of a beige map. The network has gives you equal confidence over all of the output positions. And as you let it run, you start to identify some possible moves. So you have these these 2 highlighted dots here, which is for the correct move, but you also have these 2 kind of purple dots over here, which is representing an incorrect move. You could actually move a queen if you wanted to. It's not a very good move, but you can see that the model is considering that. And if you let it run for long enough, it will eventually, that wrong solution will fade away, and it will converge to a very high confidence in the round 2 solution. Yeah.
Is that the recurrent loop?
Yep.
That we're talking, like iteration 17.
Yeah.
It's 17.
17 recurrences. Yeah.
Okay.
Okay. So neural nets can do other stuff too. I don't have a thorough study of this, but I thought I would throw this in because it's something that was mentioned in the talk this morning. No mention this is a problem that is difficult to solve but easy to verify, because typically you need search method, you need planning methods to solve these kinds of things. This is Sudoku. So we can train a model on easy Sudokus. Sudokus, their difficulty is determined by how many givens they have. If you're given most of the numbers in the Sudoku to begin with, then it's an easy problem. And if you're given few numbers, it's considered a harder problem. In some sense, the more givens you have, the more complete the problem is at the time that you get to see it, right? So we train a model on Sudokus with a lot of givens, and we test on Sudokus with very few givens. And in this case, as the method runs, all the numbers will sort of move around. And in this case, they turn green. The boxes here are the givens. These numbers will turn green. See if we can run that again. These numbers will turn from white to green when they turn correct. Most of the time, once a number is entered correctly, it remains the same, although sometimes it will change it and bring it back. And I don't know, we've spent a lot of time looking at these. I don't know what kind of algorithm the network uses to solve these, but you can train to solve Sudokus. And interestingly, all the problems, all the problems that I've shown so far use the same architecture and the same training loop. The only thing we change is the data. Even the hyperparameters are the same. So the only thing we change is the data set. But you can learn all sorts of different kinds of algorithmic behaviors just by training on these different data sets. Okay, so can we do this with language models? I thought that was the next natural thing to do. And so we decided we wanted to scale this up and do experiments on deep thinking with language models. But then I remembered I'm still poor. We're still not really able to do that. But then I went to see, I was traveling, I was in Hong Kong for the CPAL conference, which is a great conference for people interested in fundamental research related to deep learning and data science. And I saw a great talk by Dimitris Papalopoulos, where he was talking about teaching transformers to solve arithmetic problems. And this is something that he has been really excited about for years, teaching transformers to do things like addition. And I thought, that's interesting. This is a really nice model problem that we could use to study these kinds of weak to strong behaviors in neural networks. And around the same time, my student Sean McLeish was actually working on problems where he benchmarked existing neural networks on algorithmic reasoning. We actually had a project with DeepMind where we built a whole benchmark for measuring performance on algorithmic reasoning tasks. And with that benchmark, we decided we wanted to look at how good of a system we could build for solving these kinds of problems by using this kind of recurrent and weak to strong behavior. So here's a toy problem. The toy problem is addition. We're going to train a transformer model to do addition. So the thing you have to start with, though, with transformers, you have to find a way to make length generalization possible. And this is something that turned out to be kind of a challenge for transformers. Transformers have positional embeddings. And if you train only on small things, they don't see very many positional embeddings. And so if you want to test on long things that have positional embeddings they've never seen before, they don't know how to interpret those positional embeddings. So you have to be a little bit careful how you formulate these things. One thing that, these are sort of the usual tricks. One thing that is typically done in this literature is that humans like to write numbers with the most significant digit first. So when you write the number 100, the 1 is in the front. We're going to put the most significant digit last, and that's just because a causal language model, you want it to be able to start doing arithmetic when it sees the number. You don't want it to have to wait until it sees the least significant bit, because that affects all the bits that come after it, and then solve the entire problem in one shot, in one token generation. Right? So it makes things easier for the model if you put things least significant bit first. We'll do that. And you have to use some sort of positional embedding. We find that things like fire embeddings, which are designed for doing length extrapolation, and also even using NOPE, which uses no positional embeddings, also works well for length generalization. But you have to be careful to use a form of positional embeddings that allows the model to understand the longer lengths that it's going to see at test time, just from training with shorter lengths. So If we put these tricks together, you do the reverse ordering and you do the correct kind of embedding, you can get a little bit of generalization. So if we train on, so each axis here is the number of digits in one of the input numbers. So if you go to 100, 100, that means you're giving the network two numbers of length 100 and asking it to add them. If you train on length 20 problems, you train up to length 20 problems, which is this green box here, you'll see that you can solve those problems. That's what the blue means. And you can actually get a little bit outside that. You can get to 30, sometimes even 40 digits occasionally, just by doing, just because the model is able to generalize. But once you get outside of that regime, once you get to these big out-of-distribution problems here, the performance falls down to 0. So we want to see whether you could improve this with recurrence. So we're going to start with the transformer block. Nothing too fancy about it. I'm going to take an input problem, and I'm going to run it through a transformer block. And then I'm going to do that recurrently. So I'll let the transformer block run a whole bunch of times on the forward pass. And there's a trick that we use to make it tractable to solve these things on the backward pass. If you want to do a lot of unrolling here, typically you have to store the activations that come out of each of these transformer blocks, and that makes training fairly difficult. One thing that we do is we'll do a forward pass through a bunch of iterations, and then we do what's called a progressive loss, which just means that we do a backward pass through only a few of those. And it actually turns out that in most situations, you might think that you're compromising something by only doing a few backward passes here, but actually it works better than doing all of the backward passes. And I have some reasons I could go into why I think that is. But basically, you don't have to store any of the activations. You're just doing a very inexpensive inference loop on the forward pass here until you get to the point you want to do backprop to. And then maybe the last few transformer blocks, you'll store the activations and you'll backprop through that. And that gets the compute cost of training a recurrent model much closer to the compute cost of training, like say, a shallow feed-forward model. Yeah.
Talking about the training, right? Yeah. So so for the transformer, you start from some random weights. Yeah. Is that what you do? And then you go, you don't do anything, and then just adjust the weights of the last 2 or 3 layers. That's it.
Well, you got to keep in mind all these blocks are the same, right? So if I update the parameters here, then the next forward pass, all of these parameters are different too. Every block here is the same.
Oh, so you copy those?
Yeah.
Okay.
All these blocks have share parameters, right? It's just that when we backprop, we don't have to backprop through everything. Yeah, right. Yeah, and one thing I should mention, there's also an initial feature extractor and a solution extractor at the beginning and the end, like I showed before. Right? Okay. It turns out thinking can improve arithmetic quite a bit compared to feed forward. If we start train on 20 digits and we test on 40, we get about 10% generalization improvement just by adding recurrence in and letting it think for longer. And one thing I'll point out is that because all the parameters are shared between the layers, and we ended up using a relatively deep architecture to get this performance number, there's actually 10x fewer parameters in this model than there is in this model, but it still outperforms it by a pretty wide margin.
Sorry.
Yeah.
When you do the backprop, so are you thinking of this as a single transformer layer model that runs in a loop at inference time, or when you do the backprop, are you thinking the entire model is stackable?
We unroll. It's unrolled. Does that make sense? So you might think of it as a network with 20 layers, but they're all parameter shared.
Okay, so the backprop uses a network of 20 layers.
Sort of. So what we'll do is we might do a forward pass through the first 10 layers, just in inference mode. So we're not tracking gradients. We're not doing anything else. And then we'll start tracking gradients. We'll track gradients for some number of iterations going forward, and then we'll backprop through that number of iterations. Does that make sense? So we unrolled the network. Yeah.
Yes, that makes sense. That's wild.
People used to do this.
What you're saying makes sense to me.
If you were to do truncated backprop through time, the analogous thing is truncated backprop through time. Yeah. But it's easy to implement. You just basically do this in some sort of inference mode. Then you detach. You're running without gradients, or you detach the gradients, and you do the last few iterations with gradients, and then you call backward.
I have a question.
Yeah.
So it's actually for the next slide. When you do you have more blocks at inference time than you have at training time? I missed that part.
It's the same. We run the same block over and over again. So there's a recurrent block in the middle of our network, and I'm just going to let that run for longer.
Yeah. So for what you were talking about, say mazes, you told us exactly 30 times, 300 times. Here it's like how many times? How many times?
I actually don't remember the exact number off the top of my head. It's less than we did for the mazes because training these models was more expensive. We randomized a number of times. As I recall, it was like between single digits and high teens, but I forget the exact numbers that we ended up choosing for this.
And the order of magnitude between training and inference is the order of 10?
You know what? I actually don't remember that number either. But we do use more inference time compute iterations than we do train time. I just don't remember the exact numbers for this experiment. Okay. So why not 100% generalization? We rarely get 100% generalization for ComNets, and so we want to try to get close to 100% generalization here. I have this hypothesis, and we've done experiments to try to validate this. I don't know that we have anything that completely validates that this is the issue, but I still have this hypothesis that transformers struggle with what I call positional arithmetic, which means that positional embeddings are high enough resolution to tell the network that this thing comes a while before this thing. But it doesn't tell the network that this thing comes exactly 5 units before this thing. And in particular, when you're doing arithmetic, you might have to look at the position in the sequence of one digit, and then look out to another string of digits, and then figure out the position within that string of digits that exactly corresponds to the digit you're going to add it to over here. It seems like positional encodings aren't actually high resolution enough to resolve those kinds of differences in these kinds of and so if you can't succeed, then you cheat. And here's how we're going to cheat. We're going to do the usual tricks, but we're also going to do something called Abacus embedding. So we're going to take our typical representation of this addition problem. We're going to take our typical embeddings, whatever you want to pick. And we're also going to add what we call Abacus embeddings. Abacus embeddings it's just a positional embedding that tells you where in each sequence of digits each digit lies. So when you start with writing out a big number in this sequence of text, you say, well, this is position 1, 2, 3, and 4 within that number. And then you skip, you just have some empty positional embedding you use on everything else. And then when you want to represent another sequence of digits, you start 1, 2, 3, 4. You use the exact same sequence of positional embeddings. It's just a sequence of positional embeddings for telling you how far you are into a sequence of digits. That is all that it does. But giving it this positional embedding allows the model to look at these two numbers and say, well, the 3 over here corresponds with the 3 over here. And it allows it to figure out what positions need to be added together when you're doing arithmetic. And once you add that into the mix, pretty much solves the arithmetic problem. You get near 100% accuracy all the way up to and even beyond 100 digits. And so you can actually do pretty well on arithmetic. In our paper, we also talk about multiplication. We have a state-of-the-art result for learning multiplication. You just can't generalize as far. You can get up to maybe 20 by 20, sometimes 30 by 30 digits. We also look at sorting and a few other things. Okay, so to wrap up, some thoughts about thinking. I think thinking is this kind of recurrent network structure is an interesting alternative to chain of thought supervision. In some sense, you're accomplishing something very similar to what chain of thought accomplishes, but here's why I like recurrence better. In chain of thought, you typically have to train the model to produce chain of thought outputs using handcrafted human-generated examples. So for example, models that are able to do chain of thought, they're trained on problems where they've observed different kinds of math problems. They've been trained to produce a particular kind of solution that's formatted in a particular way. And because they've been trained to do that, they can use their context window as a workspace and as sort of a mechanism to do recurrence by doing multiple forward passes in order to solve a problem. But if you want to solve problems this way, you have to train the model on human-crafted chains of thought. And there are instruction data sets that do this. So if you want to do chain of thought to solve a maze, the way you would do that is you would give the network a maze and you would train it to produce one intermediate solution after the other until it gets to the final output. But the nice thing about recurrence is that you don't have to use human-crafted chains of thought. You can just train on, give it an input problem and give it an output problem, and then the network can autonomously synthesize an algorithmic approach to solving that without having to rely on some sort of human-crafted problem-solving mechanism that's in the training set in order to do it. And so I think potentially recurrence is a more powerful way to solve problems than chain of thought. I could hope that maybe this would be able to be used for solving more broad kinds of language model problems in the past. Typically, when we do chain of thought, you train the model on supervised, say, problem-solving processes for different kinds of math problems. But in principle, you could actually just train on the answer directly and allow the network to synthesize the mechanism that you need to get there. A few other nice things about chain of thought is that about recurrent systems is that they can actually do easy to hard. They're not just doing weak to strong. They do easy to hard, which means they can generalize to problems that are outside the support of their training distribution. They're not just the hard problems in the training distribution. They're actually outside the support of the training distribution. Also, I think it's interesting that neural nets, at least in principle, they're capable of learning to search and planning. We don't necessarily need to do handcrafted planning, things like Monte Carlo random tree search, right? We can observe that networks are capable of doing things like maze solving or solving traditionally search-based problems like Sudoku through end-to-end training. You don't actually need planning. I think it's actually possible to learn this behavior end-to-end. All right, thank you very much. I just want to say thanks to my various co-authors that have led some of these projects. All of these were students in my lab at some point. Micah is now a faculty member at Columbia, and Jonas is a faculty member at MPI. I know I said ARPIT. There's Avi Schwarzschild, he's a postdoc at CMU. Sean McLeish was leader of this work on arithmetic. And then ARPIT and Eitan have worked a bunch on recurrent models for solving other kinds of algorithmic problems like mazes and such. If you're interested, here's some of the papers that I spoke about. Thanks so much.
So in theoretical computer science, there is this very well-known boosting algorithm. So how do you have any thought about like how these concepts connect?
You know, I don't know if I can go way back to my beginning slides, but there's an interesting paper from a team at Harvard where they sort of consider this problem, and they say that it seems like some distillation-based weak to strong methods are sort of denoising the outputs in noisy classifiers, and it seems like that's what boosting is doing. Boosting can denoise the results in noisy classifiers, but it's hard to say that it would fundamentally succeed solving problems that are fundamentally harder than those that can be solved by its individual components. So I think boosting is in the category of weak to strong. I don't think this idea of weak to strong is new in any way. Boosting is a great example of it. But I also think that these kinds of like denoising or distillation methods are fundamentally limited. I'm not convinced that they can do the kinds of things that recurrent compute can do. When I say recurrent, I'm even including chain of thought in that category. Sure.
Thanks. Great talk. Can you give me an intuition why? So I get the difference between doing the skip and going straight through. That skipping is an advantage. But what I haven't quite understood is your intuition why working with the same layer is advantageous to trying to find different layers. What is happening there? Are we trying basically to solve too much in the other version, and that's what
I think the only thing that the nice thing about having the recurrent layer, well, I guess there's two things. One is that it gives you a mechanism to increase the test time computing. If you did feed forward and all your layers were unique, it's not clear what that mechanism is. You can try to repeat layers inside, say, a language model, and people have done that, but you're not going to get this kind of behavior as if you have a layer that is trained to be used recurrently, right? If all your layers are unique, once you're doing Resin 18, once you get to the 18th layer, there is no 19th layer, right? So if you want to have a mechanism for doing that, you have to have something recurrent. But even beyond that, it seems like the implicit bias you get from these recurrent layers is good, because even when their depth is the same and you keep it the same at train and test time, for these algorithmic problems, you actually do better oftentimes. So it seems like it gives it some sort of bias toward learning an algorithm that is good. Those are the only intuitions that I really have.
And what you just said would, I think, lead to, for problems where there is actually a better solution than other solutions, that the recurring one should lead to better solutions. Have you seen that?
Well, it leads to correct solutions more often. I don't know if they're better or not. We don't have any good way of like probing mechanistically how the feed-forward model is solving mazes. I don't know if it's better or not, but you can get higher accuracy. You can solve more problems with recurrence. Yeah. Going from over here, yeah.
Great. morning about this gap about the bit verification and generation gap. And one thing that occurs to me is problems you're looking at, you can check whether you're incrementally closer to a good solution. I was wondering if you looked at problems that are kind of classically hard to invert. You mentioned you had some results from multiplication, but let's say factoring a semi-prime. What would your intuition be for using this approach for that kind of?
My intuition would be that it wouldn't work very well. I mean, there's not a polynomial time algorithm, then no network is going to solve it efficiently either, right? There is no good solution. You might, I don't know, we haven't tried that. You might be able to learn to factor small numbers, but it's going to be hard to learn to factor big numbers. Even multiplication, it's really hard to learn algorithms for really long numbers of digits. We sort of cap out at like 20 or 30 digits for multiplication. So learning something even more complex like factorization would be really hard. Yeah.
Thanks.
Sure.
Thanks for the talk. I was wondering if you could give any intuition on how these recurrent networks compare to like diffusion models. Because when I'm looking at your maze example, I'm thinking of like, diffusion of like protein generation models. So like what's the intuition for like the difference?
Diffusion models are doing stuff iteratively as well. They're not trained. The training process is different. They're trained to solve problems in one shot. They're trained to solve problems in one shot. You give them a noisy image and then they denoise it. So they're not really trained to use recurrence. You sort of hack that in after the fact. So in some sense, diffusion models are using test time inference to increase the behavior. But I also think that they're sort of limited by the fact that they're not actually trained to be recurrent models.
So it would be like any number of cycles equals 1 in the train time.
Yeah, my sense is it would be hard to. I'm not sure about this, but there might be. My sense would be more difficult to get diffusion models to solve problems like this than other kinds of recurrent models. But I could be totally wrong about that, or I could be totally wrong about that. Yeah, still you.
So you talked a little bit. You said that you didn't sure if you know this. You talked about how you did a little bit trying to reverse engineering the algorithms the model is learning. So when you have this like single layer recurring setup, like in some sense it's like a very complicated nonlinear Markov process. Is that kind of the mathematical framework that you're using? Like obviously if you have like a transition matrix where you just like compute and steps out, or how do you like think about reverse engineering the algorithm in this context? Is there some kind of mathematical simplification?
I don't know if there's anything we can do other than looking at pictures and thinking about it. It is on some level it is a Markov process, right? It definitely is, but I don't know how much it helps us analyze it. Like for the mazes, we were able to look at the pictures, and I was actually pleasantly surprised how interpretable it was. I wasn't expecting that at all. But we've looked at a lot of other kinds of problems where I just have no idea what's going on. We even do like things like computing prefix sums and other kinds of really simple things where you'd hope to see an interpretable solution, and it just doesn't come out that way. So we can't actually always interpret what it's doing in general. Yep.
Simple question, perhaps. If you look at your using the transformer over and over again, did you have skip connections? So was it also, or that did?
There's a skip connection in inside the transformer block, so it's attention and then feed forward to the skip over the feed forward, or the skip over the entire thing. And we also have the recall / input injection thing where the transformer gets to see the state that came out of the feature extractor at the beginning. So there's actually
also present in the multiple.
Yes. So having those skip connections is important. Actually, we haven't experimented with the skip connection within the transformer block. This is kind of a standard thing, so we used it. One thing that's interesting is we've done very little architecture search. I mentioned that a lot of the problems I showed were the exact same architecture. We did almost all the architecture search on the feed-forward models, but we didn't have enough compute to train the recurrent models that many times. So we trained them once, and if they worked, then we stuck with it. So there's a lot of questions about architectures that we just haven't addressed. Architecture matters a lot. Like we've seen in our experiments, the architecture you choose matters a huge amount for the amount of weak to strong behavior you can observe. But we haven't actually done a thorough exploration of those things, other than toggling on and off the recall connections. That's the only thing we really experimented with.
So the results had the recall connections for the transformer.
Yeah.
Second question was that you showed an illustration of where you moved the starting point in the maze, and you showed a visualization of how progress it made. It was kind of freaky that it was always making progress. for a section of the maze that there's no reason for it to have explored before?
Well, one thing I'll point out is that you're seeing the solution that's extracted, but these networks actually have 512 feature maps. And so there's a lot of data that's been stored in there when it was solving the maze the first time. And it's using that data. So I guess what I'm saying is it should be, in principle, it's possible to do what it did. It's not, it's possible to do what it did. But what that information is structured like and how it stored that tableau of information and how it's extracting it and using it to recover in that situation, I don't know. But there is a lot of information packed into the neural network beyond what you see when you just look at the solution. Do we have time for one more? All right, one more.
That was really impressive. So conceptually speaking, I'm wondering. So if you consider the search problem, you have to have memory, right? Not a finite memory. However, in this recurrent architecture, your memory is finite, right?
Mm-hmm.
So I'm wondering how we can approach this. There would be problems that we wouldn't be able to solve.
Yeah. So in the ComNet case, some of the problems we're using work really well for weak to strong because the harder the problem is, the longer it is. That's not true of every problem. Chess is not that way. Sudoku is not that way. But for things like mazes, when you give it a bigger input and you do convolutions on that, you're producing bigger feature maps. Same thing for the arithmetic transformers. If you give it a bigger input, you have more activations, so you have more state to represent. So in a lot of the problems we're doing, the amount of workspace you have actually scales proportionally to the difficulty of the problem, and that's one of the reasons why we don't run into that.
Right, that was the reason I was really surprised to see that it solves Sudoku because it requires memory to solve Sudoku.
Yeah.
Also, if you want to extend that to having memory, how similar would it be to a neural Turing machine?
Neural Turing machine is closely related in a lot of ways. If you look at the original and if you look at the original Turing machine papers, it's actually much closer to chain of thought because they actually supervise the steps that the Turing machine does. So they're training it on a chain of thought to produce the solution. Architecturally, what we're doing is not that different from neural Turing machine. The difference is just that we train end to end with no intermediate steps. It's really the training process. But architecturally, there's not a fundamental difference. Yeah. All right, thank you.
The afternoon session was